I think this is a good transition. I've been leading up to it I want to talk a bit about ML weather models and kind of their history and how they work. Here's a graph for my colleague, Stefan Rasp. Stefan created, was kind of early to the ML weather space and created a lot of the benchmarks surrounding that space, which we'll talk about in a second. But here's his summary from the middle of 2024, trying to understand the progress of ML weather models. And I'd like to take a moment to annotate his maybe very coarse, not really coarse, but his bar graph, for the people who aren't following along at home necessarily. But just to explain this graph, on the y-axis you have the root mean squared error, or the error term, which is a measure of forecasting skill for a specific weather variable. In general, when you're trying to evaluate a weather forecast, there's a million things you can look at to see if it was good. But if you're only going to choose one, and there are trade-offs in everything that you choose, probably the metric that you'd look at is something called Z500. And Z is a measure of geopotential, which I believe is the effect of gravity of the atmosphere from that level of atmosphere. And 500 is 500 millibar pressure level that's right in the middle of the atmosphere. And this, trying to measure this, estimate this value 3 days into the future, that's what this chart looks like, is the best summary statistic that we have to see how good a forecast was. In this y-axis, 100 right here is as good as, this is a relative skill to the leading physics-based weather forecasting model, the ECMWF, or the European Center for Mid-Range Weather Forecast, HRES, which is their high-resolution weather forecast. In that forecast, it predicts the weather at I think a kilometer, well, 0.1 degrees resolution all around the Earth, which is very high resolution. And Will, you might remember off the top of your head the kilometer square footage.
It depends how far you are from the equator.
Right.
So
totally. So that's what this graph is talking about right now. You can kind of see this. It starts in January 2019 and it goes all the way to the middle of January 2024. So it's this rough 5-year period with a bunch of the plot dots on the plot going to the top right. But I'd like to explain this. So in 2019, before 2019, maybe the first kind of landmark is this Dubin and Bauer. These are scientists at the European Center for Medium Range Weather Forecasts. And when they were making weather models and publishing them, they saw kind of machine learning as more or less a toy, but something that would never really approach. I think a lot of meteorologists, won't throw them under the bus. A lot of meteorologists thought that machine learning would never be as good as physics-based systems. That the physics-based weather models have had 60 or longer years of investment. It requires supercomputers and lots of really great numerical methods to estimate them. And machine learning models with just a 1,000th of the amount of compute seemed of course they would never do anything better. But around January 2019, the European Center released a data set called ERA5. ERA5 is the ECMWF reanalysis 5, which is the 5th reanalysis that they did. And you'll see previously what a reanalysis means from my previous slides. It's our best history of what the weather was on Earth. And what was so great, even though this data set initially, it was later extended to cover more time, but it only covered from about the 80s to the present worth of weather. That was a perfect data set for machine learning. Instead of having to massage a bunch of sparse observations into a common frame of reference, it was a perfectly evenly gridded, I think in geospatial it'd be level 4 data set.
In terms of the zoom level. Yeah.
Yeah, what the history of weather on Earth was. And it was a 0.25 degrees resolution on Earth. So it's fairly coarse, but still really highly accurate compared to a lot of other estimates. It's a really good, especially estimate of what historical weather was. The farther you go back in time, the less direct observations of the Earth that you have. You can imagine from the 80s or even earlier behind that, there weren't satellites. There were only indirect measures. So in some sense, ERA5 is a project of archaeology in data as much as it is a scientific contribution. The next thing I wanted to show here, so you can see ERA5 being published. ERA5 was published, I think hosted by Copernicus, but it was hosted on meteorological archives, primarily like there were like tape robots that you can make an API request to ECMWF. You can make a web request to ECMWF, and then they would schedule a robot to send you 75 gigabytes at a time of this data set, and you need like petabytes of data, like a million times that order of magnitude, and you'd be waiting in line for these types of 75 gigabyte requests with everyone in the entire world to access to schedule these robots. So it's like, as important as this data set was the data infrastructure was inversely proportional to like how good it was. That's I think there are really good reasons. Tape drives are a really great medium for archival storage. But I'll talk about, I explain all this and I'll explain why it's relevant in a moment. In January of 2020, about a year later, Stefan Rasp releases WeatherBench, which is a lot of the data sets, a lot of the Era 5 data downloaded from ECMWF and put in the cloud or like in an open bucket in the format called NetCDF, which is like a traditional meteorological format. And then you see, as a result, you can see my cursor here, there are like a lot more, Stefan also published, a pretty good weather model, but these are doing about as good as chance, more or less, maybe a little bit better, a little bit worse than the physics-based systems, like in comparison, like a 50%, I guess relative score is not the same as like as good as chance, but like they're doing about half as good as the physics-based systems. Like that's, nothing you would build a forecast on, nothing really significant. The next thing I think that happened in like January of 2022, these happened like really beginning the early years, but in early 2022, the scientist, Ryan Kiesler, he basically is a guy with a GPU who has a lot of experience. He's reading the literature of what's happening in graph neural networks and modeling turbulence in like toy problems or simulated problems. And he comes up with an idea of putting a type of neural network, a GNN or a graph neural network, around the sphere of the Earth and modeling every level of the atmosphere, but making a relatively tiny neural network. And he has a paltry amount of compute compared to what a lot of like frontier labs would have, let's say. He's a guy with the GPU and an idea, and he ends up in early 2022 like getting 75% of the relative skill compared to the physics-based models with a relatively tiny amount of data and a relatively tiny amount of compute. And Ryan Kiesler's neural network totally set off a gold rush in creating AI weather models. This was the first model to prove that maybe these systems really could actually compete with physics-based systems. And then you see like developing kind of after that, the race is off, but I think like an important part, and this is related to my contribution to this, ARCO is a term that means analysis ready and cloud optimized. And Era 5 is the data set that I mentioned before. It's the ECMWF reanalysis 5. Something a team that I worked on at Google Research did is we downloaded the most of several petabytes, maybe about half of like the 12 petabytes of data that were managed by tape robots, and we put it in the cloud. But instead of just putting it in the cloud in the normal format, this format called GRIB, which like if you know what GRIB is, you can probably already feel a headache coming on. It's a really terrible format to work with. We put it into a data format called ZAR, which is a cloud optimized raster format. I think this is the stickers that you showed.
Once again.
Right.
Yeah.
It wasn't all available.
From Ryan Abernathy and Tom Nicholas from New York Climate Week. Yeah.
Totally, yeah. Joe Hammond up there and a lot of really great people at Earthmover. This wasn't I didn't initially put it up in all the data set, but eventually like ARCO Era 5 would have all 12 petabytes of all the data that was behind the archival system at ECMWF or Copernicus that anyone could use to do analysis of like what was going on in the weather, like a mirror. But the first release of it, which is a more limited release, happened in the middle of 2022. And then you can see in the middle of later on, I mentioned this too, because at the same time our team was working on, Stefan joined Google Research, and then another big player here is Stefan Hoyer. He's like the creator of X-Array, and he made significant contributions to both ARCO Era 5 and WeatherBench 2. Well, anyway, we kind of came together among a lot of others and made the data sets cloud optimized and a lot more highly accessible. And I guess I want to mention, that you can see just looking at the course view of this chart. Like the red lines are all data releases and the green lines are models. And I'll talk about a few more models in a second. But as the data becomes more available, you see much more participation in people publishing models, and much more like it's also a significant part of people's ability to iterate, and therefore I think the quality of the models that are produced. After ArcWeather 5 is released, you see like Pangu Weather, GraphCast, Fengwu, Fuxi, a bunch of other models that are doing about as good as ECMWF's model, using like maybe 1,000 or something in that order less compute, and performing about as well as these models that have been developed for 60 years that perfectly model atmospheric physics in the entire climate system. Another model I'll mention is GraphCast. I helped do a lot of the data engineering with things like ArcWeather 5 for GraphCast. And this was a significant model because it was the first neural network to do significantly better in pretty much every score that you might care about, the physics-based systems like ECMWF HRES. And a lot of other models, GraphCast it was one of the first models to beat, and now it's like one of the standard models that you compare against to see how well you do, or maybe you compare against that compared to something else. Of course, you're asking a very biased perspective here. If you ask someone at NVIDIA, I think ForecastNet is the model to beat, or other similar, more recent like ForecastNet V2 or 3. Yeah, so it's like a really incredibly exciting moment. The data precedes the models getting really good, and the models kind of create the grand challenge that creates the incentive for the data, and they kind of cyclically are related to each other like that. It's a really exciting moment right now. In particular, you see Fuxi Weather and Aardvark are two models that are new entries, and they're performing about the middle, a little slightly better than 50% on this chart. What's exciting about these models is that they're end-to-end weather models. That means that they don't, so all these models, pretty much everything else on this slide here, they are emulators of a physical system. They're emulators of ERA 5, of the reanalysis data set that's a history of weather on Earth. Aardvark and Fuxi might use ERA 5 in their training process, but they can go directly from raw observation to a forecast of the entire Earth. They don't perform as well so far, but these two models and models like it, these end-to-end weather models that go directly from observation to observation, they're the future and somewhat like the holy grail in this field. It means that we wouldn't need to have any sort of physical calculation involved at all, and that we could potentially use way more of the information available out there in Earth observation. I think a fact that's surprising to many who work in geoscience is that we use a tiny fraction, in weather forecasting, use a tiny fraction of the available data that exist about the Earth because it's so hard to fit into numerical models that we often take estimates. And I think the most promising, like the real potential of machine learning, among other things, besides being so computationally efficient, is that these algorithms scale with the amount of data you throw at them, not with the amount of compute. Like numerical weather prediction scales with the amount of compute that you throw, meaning that we potentially could throw all of the Earth observation data, all these sparse observations that we have, and potentially that leads to a really good reason that they'd figure out ways to make use of them. Potentially we can have way better forecasts than even this kind of this cluster right here of all these other weather models. And that's like why right now is a really incredibly exciting a time. Just in the last 5 years, this field has like totally been transformed by the quality of the data and it being cloud optimized, as well as like using machine learning methods, having kind of some new ideas about how to make machine learning really work for data in this domain.
Wow. So the first response I have is that I suddenly have a deeper appreciation of these stickers that I just sort of randomly slapped on the back of my phone. What's your response to the observation that we're looking at a black box?
I think this is really at the core of using machine learning for science in general. There's a really great article. I will send it to you. I don't remember the name of it. But it basically talks about the idea that the purpose of science is not to be really predictive. It's to understand. And when we use machine learning systems, they're really good at prediction. Like we can use a transformer to predict Newton's methods like 1,000 time points out, but it does it with like, millions or billions of parameters to, we can't really understand the mechanism of how they work. There are big black boxes to make that prediction versus like Newton's fundamental equations of motions are like far more elegant and simpler, and they also reflect our understanding of the fundamentals of what's going on in like planet orbital motion. That is a really significant critique, and I guess my perspective on the matter is I think we're at an era of science where we have to we're the frontier of science in general is one of predicting highly complex systems, like turbulence, atmospheric turbulence with like the butterfly effect, where like each tiny little particle makes a significant influence. We can't even begin to measure them for everything else, and it, like the effect will propagate to create a hurricane the other side of the globe. That requires that is such a sophisticated, complex system that I think actually where we might learn, where computing and science will hopefully go in the future is that we'll first start up by even being able to predict these systems, because it's like not even true, like with the methods where we totally understand every step of the way, it's unclear if we'll be able to predict them. And like maybe now we'll get to new frontiers of predicting, and then hopefully we have new methods in interpretability on the machine learning side, on mechanistic interpretability, to reverse engineer what's going on to maybe derive these fundamental principles that we can understand. And I think a corporation that's doing really excellent work in this area is Anthropic. Like they have this really great paper called On the Biology of LLMs, where they actually take like neuroscience techniques to understand these really large, big black box models. It was kind of fun. Like I have a background in cognitive science, so like I know a bit about cognitive modeling. The fun part about this type of computer science analysis or like cognitive analysis is that you can do perfect surgery on like a computer model where you can't necessarily do that on like an actual brain model. You can't turn off half of someone's lobe or something like that. But you can in these like simulated computer science systems. So I actually have a lot of faith, even though we don't know now, I have a lot of faith that we'll probably have really good interpretability techniques and understanding the circuits. I think the last thing I'll say about this, because some people might be hesitant about whether how much these are black boxes and not, is I think it really is about our level of understanding of machine learning is about a level of analysis. This is kind of like one of the first things they teach you in cognitive science. Like we know perfectly in the brain maybe we know pretty well how neurons relate to each other. Like they're more or less the Hodgkin-Huxley equations. Like we understand how like the chemical process of like calcium ions lead to a firing of one neuron, the presynaptic neuron and the postsynaptic neuron. But that doesn't mean we understand how speech emerges from that. And a level of analysis is really just about like the level of complexity that's involved in the system and how emergent behavior arises. And anyway, I guess that's why that's the kind of why I think Open Athena, like part of their banking on using foundation models for science, is I think it's like even outside of weather, in all fields of science, like I think we probably could lead to our best bet for getting to a level of understanding probably is to be even, have the competence to predict at these really complex scales.
Yeah, I mean, there's a couple of things here. Being at the frontier means you need to have certain level of tolerance for uncertainty. And, if it's offering, so the two dots you've got there on the chart are above 50. So it's, and one of them is approaching 75. So, it's doing, I guess what I'm trying to say is even if we don't understand it, at least the results are useful. So when it seems that another comment I wanted to make here is that there's a paradigm shift happening. So perhaps, we just need to keep persisting, developing these systems, and maybe the full understanding will follow. Another thing is I'm so grateful that you have a cognitive science background. That's great because the name changed from the Geospatial Index to Geospatial FM occurred with an episode recorded with Nelson Roque, who's a cognitive scientist at Penn State. And that was deliberate because my view of artificial intelligence, because my first degree was psychology, is that there's no intelligence going on. I'm sorry. And so, yeah, I loved you starting to get into the mechanics there of synaptic firing. And we need more of that, I think. And it reassures me that there's someone with that kind of a background in you engaging in this. So yeah, looking forward to the next slide. I think we've survived this one, and I've drunk half my cup of coffee just to get through that.
I'm so sorry. I'm working through my cup of coffee. So I've talked about this huge amount of advancement. Like all this is relative to physics-based systems, and now machine learning-based systems are beating even ensembles, like even uncertainty injected into guesses. And I wanted to talk about it at a really high level, like the 10,000 foot view. How is this possible? Like what's really going on here? And maybe one of the famous kind of oldest toy examples, we all know that weather involves chaos. It involves a chaotic system. And one of the most notorious examples of chaos is something called the Lorenz attractor. And this is the code for the Lorenz attractor. It's actually relatively small, and you can see it's kind of like multiplications and addition on top of 3 variables. And then more or less what you do is you take a few initial conditions. So these are like a point in space that this starts at. And then all you do is for each steps, and this is maybe several thousand steps, you say the next step is the current step plus this math here times like the change in time. So the idea here is that the next point in the Lorenz system is dependent on the previous point in the Lorenz system to infinity and beyond. Lorenz, this actual mathematical model, what these x, y, and z variables are modeling are, I think, actually like the convection or the movement of heat in like a glass of water in an idealized system. So it is like the tiniest toy example of what chaos and weather can be like. And the famous idea from Lorenz is that if you take, even though you totally understand and can totally predict, you have a total understanding of the function of the transformation from each time state from point A to point B, time 0 to time 1, this is a totally perfect model, even with relatively tiny changes in the initial condition. So this is 0.00001. If I ran this again and did the perfect system, very quickly I wouldn't know if this line was in the right hemisphere of like the butterfly or the left hemisphere of the butterfly of the Lorenz attractor. And it would be up to like on a long enough accumulation of error, we really wouldn't know how to predict it. And all numerical weather systems are basically like this, like where what they involve, why they scale with compute is that they have more or less like this loop. I call like numerical weather prediction calculus inside loops, and that more or less is what you see right here. So you have this relationship where you're iterating through steps, and the next step, XYZ's I plus 1 is equal to the current step, the variable I plus the difference, a delta on the function. Like that's all that's happening here.
This is reminding me of agent-based modeling, the game of life, from actually the coursework part of my master's at the University of Melbourne. That was in a 2D sort of sense. It reminds me of that concept, at least.
That's interesting. I never made that connection, but I totally could see it. Where the game of life is about a few simple rules, and then you're iterating through it. I could say, like, you probably could say that it's a chaotic system in a discrete space, the game of life, where you have a few simple update rules, and then it's about applying things in a loop to initial conditions. So I do think the game of life is dynamical, and I think that's a lot like life. Dynamics, which is referring to what I call dynamics is calculus in loops. Like this is what's kind of that the fundamental of what's going on. I think for both what happens in like numerical weather prediction and in the game of life. That's a really cool insight. Thank you for sharing.
Okay, so is the Lorenz attractor, is this a formula or a mathematical approach that's what the physics-based models are based on?
So Lorenz was he was a mathematician who basically came up with the idea of chaos and the fundamental limit of predictability in chaotic systems. And like this equation, I don't have a visualization of it, but I really could. Like, it's like if I added, instead of 0 here, 0.00001, and I ran this perfect system, like ran this code, I would get a wildly different trajectory of this line, as you can imagine. And the idea of chaos, Lorenz kind of coined the definition of chaos. I remember, and a math historian will totally correct me. It's like the idea that setting the initial, like even tiny perturbations in the initial conditions means that the system is unpredictable. And why I mentioned this equation in particular is it relates to the limits of what is predictable in toy problems, but also in weather and what is possible numerically. In addition, what I like about this toy equation is that it explains what it means for numerical weather prediction to scale with compute as opposed to scaling with data. So like, what is actually happening in numerical weather prediction is that they're having a small delta t and simulating forward in time with taking into account the previous step. They're simulating all the intermediary states of physics with like a full physical understanding of all the intermediary states. You know, I think probably the reality of it is a lot more complicated than that, but more or less like that simulation is what is so computationally expensive and what has to happen in so many computers. So underlying this change, this little like 2 lines of Python right here of the calculus inside loops part, you can't run this on GPUs. And like, one perspective on what machine learning is it's really the same type of numerical methods that we had before, but it's designed for modern hardware. And the way hardware works today on graphics processing units is that they're stream processors. You can take, there's something called SIMD or single instruction multiple data, where you can take the same operation and lots of different data and run it 1,000 times, like 1,000 threads or maybe more, the same operation over and over again. And one way of looking at what a GPU is that it's a supercomputer on a single chip by taking a lot of the worker threads, maybe with a lot lower memory bandwidth, but still applying lots of operations all at once and having them asynchronously kind of all do the same operations in coordinated. That's kind of how a GPU works. You can't do this type of numerical calculation on GPUs because because it's a stream processor, because it's fanning out the same instruction over multiple data. I always need the previous step in order to calculate the next step. I need the next step is the previous step to the next one, and I can't divide and conquer that. What machine learning does is it figures out how to take advantage of this hardware speed up, and it automates the invention of the calculus so that you can basically, instead of like getting all the intermediary steps where delta t is small, I can predict it. Machine learning, like neural networks, are universal function estimators. So like they can estimate any sort of function as long as you can describe an error of a function. So the way they work more or less is instead of calculating every intermediate step, they're good estimators for the end result step that you would want starting from the first step, as long as you provide a sufficient amount of data. Do you have any questions about this slide before I go to the next?
I am barely keeping up, I'll be honest with you. So you're using this slide to set up the contrast between how things have been done in the previous scatter plot chart from that ERA5 model in using data from 1979 to 2020, was it? And because I asked you how the Lorenz attractor, what process uses it, and I still don't understand.
Lorenz is this shape of problem, like here's physics, like perfectly understandable physics. This is like talking about convection or heat. And then here's it applied in a numerical process. The next step is it depends on the state of the previous step, integrated over time. That is the rough high-level recipe of all of numerical weather prediction, as I understand it.
That's what I'm trying to. Okay, great. Now I'm starting to. I needed you to describe it that way.
No, thank you for asking, because I don't think I established it. Like if you wanted to summarize numerical weather prediction instead of predicting a million things using sophisticated, 60 years code bases, you might explain it in these like 50 lines of code. Like this is like 6 lines. this is like 2 lines in a loop, and then it's some setup. Like the simplest, if we were to extract all the complexity and put it into its simplest form, you'd think that we'd be able to predict like what the weather would be like the heat, whether the heat's going to be hot or cold, let's say, depending on the X and Y axis, in like 100 or 1,000 time steps. You think that if I knew the current conditions and I knew the perfect governing equations, I'd be able to tell you with certainty in like 10,000 steps, it's going to be hot in this part of the cup of water. And what Lorenz found is that no, this is not possible. And the reason it's not possible is because there's what kind of the definition of chaos is that in this update step, there are accumulation of errors that cascade. And so too, this directly applies to the error. And this is like kind of a somewhat related to the
those errors can't be deterministically kind of modeled. Is that the point?
The idea of chaos is that even when you have a perfectly deterministic system, unless you have a perfect way of measuring every tiny detail to like actually surprisingly small orders of precision, it will be unpredictable.
Okay. And those will accumulate to a massive degree. So there's a huge amount of drift.
That's right.
Okay. All right. I think I've got my head around enough of this to advance to the next slide.
Okay. I want to talk about like that understanding of chaos is that specific Lorenz toy problem, the Lorenz attractor, and Lorenz's idea of chaos actually is very concrete. It's cool for the understanding of mathematics and the strangeness of the universe in general. But Lorenz is specifically talking about the weather, and Lorenz, he was known for having a limit of atmospheric predictability of how long we can predict the weather. And he later backtracked, like maybe it's possible, but it's been kind of like the unstated rule in meteorology that the farthest we would be able to predict the weather is 2 weeks. And you see this in every 10 years of advancements in numerical weather prediction systems. You see about like 1 day of lead time of forecast skill. So like 10 years of development, instead of a 14-day forecast, you see a 15-day forecast.
Is this because it's the European Center for Medium Range Forecast? Is medium range 2 weeks?
The medium range is about 2 weeks. It's like 3 days to 2 weeks.
Okay.
And like a short range or whatever, often called a nowcast, it's like minutes to 12 hours. And
gotcha.
That's a really good context. That'll come up later in my presentation, assuming we don't run out of time.
It's fine if we do. We can have another.
Totally. Just, this is your whole podcast now. Just
and that's fine with me. This is fascinating. It's such a privilege, Alex.
Researchers at the University of Washington asked themselves, what really is the theoretical limits of predictability? Lorenz, like, kind of unofficially set the limit at 2 weeks. How good could in the age of machine learning, how far in advance could we predict the atmosphere only knowing the initial states of the atmosphere? And this is the result. I'll explain the results first. So it was thought that let me explain this chart. So in the y-axis, you have loss, which is a measure of error. Loss is associated with the amount of error in a prediction. And the x-axis is lead time. So from the starting point, 0 is the starting point. How many days in advance do you have a certain amount of error over time? And you see up to 15 days, there is very low error. And this is like what is known is the limit of what is predictable. And if you look at the black line.
Just for the benefit. Okay, you're mentioning the colors of the lines now. Great.
Yeah, there are 3 lines. And you see there's a lot of like fuzzy lines. I'll explain that in a second. There are 3 main lines. The black line is, I believe, like a traditional control forecast. This is like a numerical weather forecast. And the black line goes 0 to about 15, the 14 days, and then the error gets above the loss, or the error gets above 50%, and it's like much less skillful. The green line, which is, it looks like a one of their toy forecasts that they optimized for, that they saw how theoretically possible it could go for. It starts to have error around 15 days, but then it has much less error going all the way up to like 30 up to 40 days. The red line, which is something they call a 32-day optimized line, it has low loss or low error all the way up to, if you look at it, like kind of below 50% for like 32 days. like a month of time, lead time in it, ahead of time, and then eventually goes off into having error.
So that's a doubling of what Lorenz said should be possible.
It's a doubling of what Lorenz said is possible. And this paper, testing the limits of atmospheric predictability with a machine learning weather model, what they did was, so one of the advances, the implementation detail of machine learning, how machine learning works in general is you guess, and then you see how wrong you were, and then you correct. And part of the mechanism for correcting is something called automatic differentiation. Differentiation means it's a type of it's calculus. It means you can calculate a derivative, but you need to calculate the derivative that's the core mathematical operation that is part of calculating the amount of error your parameter, or the amount of error of the guessing system was with respect to the feedback that you got, and how to distribute that error to the system that is trying to give the answer. That I basically explained in 30 seconds what backpropagation is, if you've ever heard that term.
Something that's come up for me in what you've been talking about, does machine learning account for chaos?
Machine learning systems, I guess this is what this slide is talking about, is that machine learning systems can learn any sort of function just as long as you have a good teaching signal for it. It doesn't care what the internal methods are to get to a function. So it doesn't know this equation. It has figured out a way to automate creating this equation, so long as you have a feedback signal and so long as it can make the error as low as possible. So machine learning systems and toy problems have been found to do really well at predicting chaos. When you create a toy chaotic system, like literally the Lorenz attractor or other types of systems in multiple dimensions, like more than 3, in toy problems, it is really good at predicting chaos. It was only a matter of time before it was on a real world chaotic system like the weather in some respect. And I could explain how this works, but because of this property of machine learning doing well in chaos, and this idea that via the backpropagation algorithm of neural networks, that a machine learning algorithm is fully differentiable, what Trent Vonch and Gregory Hackham, and I don't know these people, so I'm totally butchering their names. What they did is they used this property of neural networks to figure out what were the ideal initial conditions in the input. Because like our reanalysis, like error 5, it's just a best guess and it doesn't know. But what they did is they figured out, looking at the very end of the network, they went back in time and are kind of like in here, I say these initial conditions, this XYZs, these XYZs, these have initial conditions 0, 1, and 1.05. They figured out how to make these better while keeping the networks the same. And the value of doing that is they could see, if you optimize the initial conditions and kept the network the same, what is the theoretical limit of how far in advance we could predict just by having ideal initial conditions. And basically they proved they didn't create a weather model that was really good. They proved that our weather models could be substantially better. Like the 2-week limit that Lorenz set out is kind of more dogma than actual real hard limitation. And in theory, our weather models could be as good as predicting a month in advance just with a knowledge of state of the atmosphere.
So trying to keep up here. Maybe a better way to put what I was trying to say is that the machine learning approach is somehow robust to chaos. And I like that you said basically it guesses and it checks the difference between what was guessed and what is observed. Is that a good way to put it?
That's exactly right. I think that's a very astute description and observation about how it's doing it. Because it doesn't have to simulate every intermediary time step, and it's just being a really good estimator, it is robust to chaos.
I've gotten to the bottom of my cup of coffee here, so all right, showing the results.
Going back to this slide, I think that implication is correct. I need to understand the paper a lot better. It's it's more on the NWP side than my background is prepared for, but I believe that is probably a correct implication of the methods of these two researchers at the University of Washington, is that we could it could make our ground truth a lot more accurate, because it could make our not our ground truth, but it could make our history of what the weather was probably more accurate based off of new methods of being able to, like, calculate the error, like introspect about how good a prediction was. That's a really interesting insight never considered before.
Okay, so again, playing the advocate here of the layperson, and I'm not playing it. I am the layperson. So, for my benefit here, can you go through the point about guessing again? Can you explain that?
Yeah. I am thinking whether or not I want to like create a toy neural network or whatever. If I had a whiteboard, I would draw it on a whiteboard, but I'll try to describe really vividly for the sake of the audio listener. We all remember y equals mx plus b, right? It's a line of best fit.
It has been so long since I was involved in it.
let me restate that. You have
this is differential equations, is it? Or
no, this is,
oh my god,
this is algebra, not even linear algebra.
Oh my god, oh,
I know.
This is decades ago. I'm so embarrassed, but this is important context for you, because I'm coming to this, Alex, without physics.
just for all the people, like, this is all fresh in my mind, but I once like failed a software engineering interview because I couldn't remember y equals mx plus b.
Oh wow.
But I was doing all this geometry stuff, but it was just like, I felt embarrassed about it after the fact. It's totally okay.
Don't be
embarrassed.
You're
okay to be rusty and all this. Like, you probably are using it without realizing like how to write it down in the mathematical notation. I think that's a beautiful thing. But imagine you have like on the y-axis square footage of a house, and on the x-axis you have number of bedrooms, and that's discrete. And you can imagine if you plotted a number of houses in a market, let's say in San Diego, that's where I'm from, you would see kind of a rough correlation of the square footage of a house and the number of bedrooms of the house, and then, like, let's say one thing it predicts is the price of the house, right? You're trying to estimate those things. So this is kind of complicated. It's already 3D, but you can imagine like the color of the plot of line is like, or the size of the line is how expensive the house is. The bigger the dot, the more expensive. And then you have these two types of things. You're trying to predict, if you know the two inputs of the number of bedrooms and the square footage of a house, can you create a good estimate of like a rule of how expensive is the house? You need to know this because you're in the market and you want to get the best house that you can, or understand if you're getting a good deal or not. And you could like do a perfect equation that just perfectly estimates it, or you could do what machine learning does and draw a random line. You draw a random line, and then the core feedback you have is, how close is this to how bad of a guess is this? What you do is you measure the distance from each of those points. You can just directly measure the distance from the line. There's an equation that does that. And what you do is, if you can measure the distance of every point to the line, then you can sum all those up. And there are negative numbers because sometimes the line is above the point. So you square root it.
This is the root mean squared error.
This is root mean squared error.
Yeah.
And so what you do is you guess, you see how wrong it is, and then you increment the line. Specifically for a line of best fit, the two parameters you have are the y-intercept, where the line crosses 0 on the x-axis, and the slope, the y equals mx plus b. That's your parameter 0 and your parameter 1, or your bias and your parameter in machine learning. And machine learning is a process where if you have a teaching signal and you have a model that has parameters, a parameter is a knob or a dial that you can turn. Machine learning is in a loop. You guess, you see how good it was, you get a teaching signal, and then you adjust the knob, and then you guess again. You do that forever until it basically stops. That's the core of machine learning.
Yeah, but there's a certain whimsy to this. Excuse me for using these terms. And there's a deliberate imprecision in it. it's counterintuitive because a lot of outsiders, they think of physics and mathematics and it's all very conservative and there's a lot of certainty. It's very deterministic. But I love the fact that it's throwing spaghetti at the wall, seeing what sticks in a way. And I love that this approach has led to a doubling in what was thought possible in terms of the range of prediction. So
there is whimsy, and it is like much to I think probably many generations of mathematicians and scientists having disappointments that the person who just stacks more layers on a neural network or whatever ended up outperforming their like years of research.
Yeah.
You even see this in the natural language processing. Like you see people coming up with these sophisticated understanding of languages, and all that someone did is make one model really, really big. Like GPT came out and it ruined like decades of researchers' work and intimate things. Like it turns out that if you have a big enough language model and you just basically did what I said, but to huge amounts of scales of data and compute, it did better than everyone's specialization. Like my colleagues, were like all of my years of research were
right. Yeah.
done away with. Yeah. It's kind of a crazy thing. So it's like, even the machine learning people feel that effect from machine learning. It's not just scientists or whatever having the machine learning people come after them.
I'm glad we can inject a bit of humor and levity into this, and that there's what can I say? There's a bit of this branch of science seems a bit rebellious, and I think that's another thing that a layperson can latch onto and maybe identify with here. So yeah. Thanks for that latest installment, Alex.